Hello again. So in this video I will guide you through a lesson, more of a practical lesson to tell you about different model paradigms that we can use in order to program or encode or code a software for a satellite. So I'm using Code Composer here. In Code Composer, I will create a new project in new CCS project. Let's call it my satellite. So in this project, I have a lot of files. I have my main file. If I want to use, that's what we call a infinite loop paradigm, which is very simple. I would write my code right here, the main code would have two parts. So one part that is specific for configuration, and one part for the infinite loop, which will run forever. So in this first part is where we code the bootloader. So this is supposed to be like the procedures of the bootloader, where you have to check if the satellite has booted an even number of times. You have to check if the peripherals are all in good health. You have to initialize all the buses, all the communication buses, if you're not in safe mode, and etc. So this is where you place this kind of code. For example, if I want to configure a simple task here, let's configure a timer. The same timer that I showed in the video. Like for instance, the timer A0. I can configure this timer by setting up the counting mode to up mode and selecting the clock to a slow pace clock, let's say a clock. For this specific timer, I will make it count 1 second. So I will use the threshold 0, which has that special meaning of ceiling of counting. The ceiling will be 1 second. So for a clock that counts in a speed of 32 kilohertz, if I count to 32,000, it will be the same as counting to 1 second. So I always decrease 1 in this counting, because remember, we start to count from 0, and if we want to reach a specific number of clock cycles, I have to use that number minus 1. So this should count 1 second. So how are we going to use this? So configure timer A0. Let's use a LED just to know what we're doing. So I will configure the red LED to show you guys just a quick, just to show you how do you use this. So let me configure the output pin of the LED as an output, and let's start. Let's write a 0 to this bit value. So this operation is called bit clear, and this operation is called a bit set, and this operation right here is called a bit clear. I'm clearing and making this bit goes to 0. So the output, the LED will start off. And if I want to synchronize my code with the timer, I would set up a pooling, a execution block right here. So I will have to check if that flag, the corresponding flag of that event, of that hardware event, is going to 1. Remember, to use the flag, we don't actually need to use interruptions. So the interrupt flag can be used without interruptions. And that's what we're going to do here. So I'm going to check by filtering only the capture and compare IFG, which is the corresponding flag of this timer A0 channel 0. Let's check if it has reached 1. So this loop right here will stay in infinite loop while this flag is 0. And when this flag goes to 1, this condition right here will be false and the loop will exit. This semicolon here is the same of opening and closing brackets. But to make the code simpler, I am going to just use a semicolon at the end. So every time this happens, I'm gonna toggle the state of the red LED. And let's see if that works. So this paradigm, see this programming paradigm is called infinite loop because of the way you program the infinite loop right here. So you have a configuration step and then an infinite loop right below. So I'm gonna hit play and I'm gonna show you in my screen the effect of this code. So this is the board. This is running. Oh yeah, we forgot to clear that flag, right? So we have to clear this flag always after you check the flag, always after a execution loop. Wait 1 second, clear the flag and toggle the state of red LED. So let's try again. So the red LED is this LED right here below on the bottom side in the left. This one right here. So as you can see, the red LED is actually blinking in a period of approximately 1 second. So great, that's exactly what we wanted. So this paradigm is called infinite loop, but there are other paradigms. When you use interruptions, things can get a little bit simpler, and you can easily put more tasks and background tasks on the infinite loop. So let's keep the infinite loop right there, and let's make a different task completely separated. So for instance, if I wanted to blink another LED in a different frequency, it would be kind of hard to do it in the infinite loop paradigm model. So I would have to use an interruption. So let's port this code to an interrupt model. So instead of doing this in the infinite loop, let's use an interrupt. So I'm going to configure right here a CC interrupt enable to enable local interruptions. So, and then what we have to do is setting up the global interrupt using enable interrupt. Usually this line goes in the end of your configuration. It's the last thing you do before entering the infinite loop. So this will allow the processor to see the interrupt flag coming whenever it goes to 1. So when I enable this interruption, I have to code the interrupt service routine to use this code inside the interruption service routine. I'm going to do that right below here using a pragma. So in the vector, I'm going to set up the timer 0 A0 vector, which is the vector for this interruption. I'm going to set up a interrupt service routine with the name TA0 CCR0 ISR. Remember, interruptions, they don't have any input parameters. And I'm gonna use this code right here inside the interruption. So this is the event-based task that I want to implement. I no longer need to check the flag. I no longer need to pull the system to check if the flag is going to 1 or going to 0. This will be done automatically right here. So let's check if this code works, if we have exactly the same behavior. So just to make sure we're using a different code, I'm going to blink the LED 2 times faster. Let's see if it works. So let's count half a second. So right now, I want to see the LED, the same behavior of the LED, which is happening right now. It's blinking 2 times faster than before, and it's using actually the interrupt right here. So this code, this function right here, which is not a function, it's an interrupt service routine, is being called automatically by the hardware event. This is not being called anywhere in my code, right? So I just configured the interrupt locally and globally, so that this code can actually be executed. And whatever is in the infinite loop, it's called a background task because it has lower priority than my infinite loop. All right, so this is an interrupt-based paradigm model of programming, let's say. Right, so the processor is not doing anything useful when it's on the infinite loop. So why don't we just turn the processor off, right? So let's use a low power mode instead of entering an infinite loop. This should be fine, right? So low power mode, when you call low power mode, it will not only set the low power mode, but it will also enable interrupts, because the only way you can exit the low power mode is using interruptions. So it will automatically enable interrupts. So I don't need this line right here. So instead of the infinite loop, let's put the CPU to sleep. So this is very interesting because this has exactly the same behavior as before, but I'm going to save a lot of energy by doing this. Unfortunately, this board right here, this development board, doesn't have energy measurement utilities, but I have another one that has. I could show you, but it's with a student of mine. So let's try this code. Even though the processor is in sleep mode, the LED will still blink, hopefully. So as you see, the LED is still blinking, which is great. And we have a more economical from the energy perspective. All right, guys. So these are 2 different model paradigms. I hope my screen didn't block my coding session right there. But anyway, so there is a third model paradigm that I want to show you guys, which is using a operational system. Let's say you want to put into the microcontroller a very simple operation system, because you know the number of tasks, the number of things that you have to do in your system is so huge that you need another paradigm, completely different. So an operational system will manage the creation and the deletion of tasks. So you can create tasks in an operating system by creating as if they were functions, and the operating system will then schedule them in a specific time window so they can execute. And you will have the impression that these different tasks are all running in parallel, which is great because you can, stack a lot of tasks in the same processor. So let's see how to do this. For this coding session, I'm going to use FreeRTOS, which is a very popular a very popular operating system. It is a real-time operating system. What does that mean, a real-time? Usually when you have a real-time operating system, it means that the tasks, they have a time to be completed, which is called a deadline. So if they don't complete in that deadline, they are considered to be a failed task. So let's download FreeRTOS right here. I'm gonna download the source code. So I'm saving the file. And when you save the file, I already downloaded it. So I'm gonna extract the code and show you the... So it's right here. Let me show you what's inside this folder. So when you download FreeRTOS, you have a folder with a lot of information. So you have the main code of the FreeRTOS right here, which is the operating system. Then you have this FreeRTOS Plus, which is basically the extra parts of the system. You don't actually need this, but it's very interesting to know what is right here. So if you see the source code, you have access to network layers like TCP, UDP, traceability, which is great. Some other important things like connection to the Amazon Cloud, AWS. So there are very nice and great utilities here that you can use. And this is community driven, so there are a lot of plugins out there that you can download as well. But I'm going to show you specifically the source code of the core of the FreeRTOS, how to make it work. So this is the source code right here in the folder source. I'm going to copy this to my project. So let's go back to our project. Let's copy this code to my satellite project. So I've called this project My Satellite. And FreeRTOS code is right here. So I'm going to rename it as FreeRTOS, right? So FreeRTOS folder now has a lot of things that we need to check. So when you open the FreeRTOS folder, you have the source code of this operating system, which is it's a very simple code. And you have a folder called Portable, which is the portability code for this RTOS. So you have code for different kinds of architectures, different kinds of microcontrollers and microprocessors, and you just have to select the one that you are going to use in your project. Since I'm using MSP430, I have to find a suitable project right here, a suitable architecture. And the architecture, the portable part of the code, it has to match not only the architecture of your processor, but also the compiler. Because for this microcontroller here, there are some different compilers. We have Texas Instruments, which is the developer of this microprocessor. They have their own compiler. GNU, GCC, the famous GCC compiler. There is a branch for this microcontroller. There is a compiler from IAR, which is another compiler by itself. So you have a lot of different compilers for this architecture. Since I'm using Code Composer Studio, this is the folder that I'm interested in. So I'm going to erase all the others. So there's another folder here that you have to keep, which is memory management. So memory management is something that you want to keep because sometimes you want to allocate memory and you want to keep this folder right here. So let's keep only these two folders and I'm going to delete all the others. So in the CCS folder, I have also different architectures. I don't want to work with ARM right now. I'm working with the MSP430X. So let's erase these folders too. Now that I have only the code that is for my microcontroller, I can now start debugging and compiling this code. So when it comes to memory management, FreeRTOS offers 5 different types of memory management for the malloc function to allocate memory dynamically. So these different functions, when you are in level 1, you can only do static allocation, which is okay. Most cases just use that and that's fine. From heap 2 to heap 5, you have dynamic allocation with different resources, like in blocks, in dynamic blocks. It's very interesting to see this, but I will invite you guys to look at the documentation to see what's the difference. I'm going to choose one randomly. Let's say we use heap level 4, all right? and I'm going to disable the other ones. So I right click the selected files and select exclude from build. Or you just delete it if you want. So now I have only the files that I want to compile. But FreeRTOS require one more thing, one more file, which is a configuration file. This file has to come in the main folder. It's a header file that you include to configure the whole system. So I'm gonna share with you the most simple file that we can. So let's create a new file here. Let's say it's called freertosconfig.h. Okay. So for this configuration file, let's just first protect this file against multiple readings. So let's use a if not defined freertosconfig header, define this symbol so this file won't be read multiple times. And I'm going to share you my minimalistic configuration. So first we have to configure the scheduler. And to configure the scheduler, there is a macro that's called config use preemption. So the FreeRTOS can use two different schedulers, a cooperative one and a preemptive one. The preemptive is the one that we want to simulate, to emulate parallel behavior, because when you preempt a task, it means that you interrupt its functioning to include another task. So it will switch between tasks arbitrarily. In cooperative scheduler, it's almost like there is no scheduler. One task will execute only when the other one has finished, or it will then pass the token to the other task. But let's use preemptive, which is the most common way. Then for each task, you can have different priorities. I'm going to use a max priorities of 3, because we have not so many tasks and they will mainly have the same priority. Let's define the stack size. So config minimal stack size is the number of words in the stack for a given task. We need some configurations. FreeRTOS is all configurable, so you can add functionality even to the scheduler if you want. But I'm not going to use those configurations. They are called hooks. For instance, you can use an idle hook. Whenever you go into idle state, you can use a function to program what's going to happen when you go into idle. I can also program a tick hook. Every time there is a task change, I can program something. So this, I can actually modify the behavior of the scheduler. So this is great from a configuration perspective. So you also have to configure the heap. So the heap is part of the memory that is going to be used to allocate dynamically memory for the different tasks, for the different objects of the system. And it also has a 16-bit tick, but we're not going to use that. So we don't care. Also, let's include some goodies. I would say task delay is an interesting function to use. You can include, so since this RTOS is very configurable, everything that you use in your system, you have to include in this config file. So I'm going to use in this example the delay, just to show you how to blink a LED in an operating system perspective. And you also have to configure a tick vector, which is the interrupt that is going to trigger the scheduler. In this case, I'm using the watchdog timer vector. All right, so this is the minimal configuration that I can get. Now that we have the configuration, let's go into the main and see how does this work. So in the main, good let's say, a simple, the traditional way of working with operating systems is that first we have to include FreeRTOS.h, which is the header of FreeRTOS. But this header right here, to use FreeRTOS, you have to include in your files. But to include it right here, you have to edit. You have to add the path to this file, and this file is in the FreeRTOS folder under include folder, which is right here, FreeRTOS.h, which with caps F. So to do this, actually we need to go into properties here of the project and add that folder as an include folder. So I'm going to add this folder right here. So my satellite FreeRTOS include, so this folder right here, to the include folders of my project. All right, so this should be good to go. I can include using this symbol. So now let's configure the system. So the main, now in this different paradigm, the main is just a function that will configure the system and boot the scheduler. So this is only the bootloader. The main is now only the bootloader. So we have to do some things first. So ideally, the bootloader will configure all the peripherals and end by creating tasks. We have to create tasks, and finally we will start the FreeRTOS by calling vtask start scheduler. By the way, this function right here is under, if I recall correctly, under task.h. All right. So how do I create a task? So to create a task, I will call a xtask create. So a create is a function that will allocate memory for the task and will run the task. So the task has a name. Let's say we want to blink the red LED, and this is the name of the function that we're going to create. This is a debug information, the text name assigned to the task. So this is just to locating the debugger of the FreeRTOS. So you can allocate different sizes of the stack. I'm using the minimal stack size that we used in the configuration. And then you can pass parameters to the task if you want. You can assign a priority to the task. Since we only have 3 levels of priority, I'm using the middle one. And then you have a task handle if you want to control this task after creation. So, all right, so this is it. You also need to configure the watchdog, which is the timer that will run the system, that will run the scheduler. So if we take a look at the portable part of my code, inside port, there is a interrupt right here. It was written right exactly how I've written my interrupt service routine before, with the pragma and the interrupt right before. And it will use a config tick vector. So this config tick vector here, we have used a watchdog timer vector to configure the scheduler. But now I need to configure the watchdog timer to use interruptions. So we need to do this in the configuration part, which is called the application setup timer interrupt. So we need to code this function right here. So to code this function, let's do it in the main function. Wherever you program it, it's fine. So let's code a function that's called application setup timer. And inside this function, you have to configure the timer that's going to wake up the scheduler to do the scheduling. So I'm going to configure the watchdog timer using the watchdog password, using this low clock, and setting up a interval of 2 milliseconds. So set up 2 milliseconds tick And also we need to use the interrupt enable. This is a local interrupt enable to start the scheduler. And we don't have to worry about setting up the global interrupt enable because it's going to be configured in the start scheduler right here. So that will be done for us. So, all right, I think we're done. Let's test the system, right? So I'll just create this blink LED function here, and we're good to go. So the prototype of a task starts with the name of the task and the parameters, PV parameters, which is how you pass, it's a pointer to an object that holds the parameters of your function. We're not going to use this because this is a very simple function. But this is the prototype. So I'm going to do exactly what I've done in the previous example. I'm going to set up the LED in a configuration phase. Configuration. And then I will set an infinite loop right here. An infinite loop that will always blink the LED every 500 ticks of the system. If my tick is 2 milliseconds long, 500 ticks will give me about approximately 1 second time. So this will make the red LED blink every second. So let's see if this code works, right? Maybe, let's see if it works. So I'll compile. Oh, of course, we have to correct the compilation errors because not everything is perfect from the start. Right now I have some errors. If you check the errors right here, you say I cannot find the source file, which is portable GCC RL78. So this code right here is not generic. You have to put the path of your portable code. So my portable code is under CCS MSP430X port macro. All right. So let's see if there is another error like this. So this is an error. It's saying include FreeRTOS must appear in source files before croutine. All right, so this is in the header of croutine. I'm going to look in the source code of this croutine. It's a coroutine. It's a resource of the code of the FreeRTOS, which is very interesting, but we're not going to use here. So it's saying this header must go before croutine header. So let's make this change. It's easy to do. Let's compile again, see if it works. Great. So now it compiles. Let's see if it works. I will debug, so let me program my microcontroller. So this debug, I'm sending it right here. So this is the main code. So let me show you the microcontroller, which is right here. Let's see if this works. So I hit play. So now you see the LED blinking at almost the same frequency. It's funny. It's always the same example, a very simple example, which was made in 3 different paradigms. So using an operating system, using an infinite loop, and using interrupts. So this is how you do it. I want to add a new task which is independent of that one. Let me control the red LED in a different frequency. So in an operating system, this is very easy to do. This is very simple to do. So you can just create a new task. So let's say we're going to blink the green LED. Instead of red LED, I'm setting the green LED here, green, which is in pin P4.7. So let's try this. And let's use a different frequency. Let's say 250 ticks for this one. Now let's register this function. Let's create a task for it. So instead of red LED, let's say this is the green one, green. And that's it. So let's see if this works. So two independent things will happen here. So you see the red LED is blinking at a frequency and the green LED is blinking at a different frequency. This should be, well, not difficult, but tricky to do in an infinite loop. Easier to do in interrupt, but extremely simple to do in an operating system. So this is it, guys. I hope you liked this presentation. There is one thing to be aware of when you do this kind of things is the total memory that is occupied by your code. So if the total memory that is occupied is depending on the heap size. So for instance, if you use a heap, a smaller heap, when you compile, you see that the memory allocated for that heap, it's much lower. So the space used in the RAM memory depends on the heap size that you use. So there are a lot of parameters, a lot of things to learn in the FreeRTOS. This is just an overview. I hope you enjoyed it. And I hope you liked it. If you have any questions, so don't feel free, to send me an email on my personal email, which is in the institutional email, which is dcafe. So from Daniel Cafe, dcafe@unb.br from Brazil. All right. So with this, I would like to thank for your attention and see you next time. Or have a nice course and of course for you guys there. Bye bye.